Options exhibit a certain symmetry, which simplifies the work we need to do to understand the Greeks of a put option. This is thanks to put-call parity. First, let's think about what would happen if we took a long put option and combined it with a short call option, with the same strike price and time to expiration. Well, that just looks like a short position in the underlying. In fact, it doesn't even matter how long until expiration. Both the at expiration and prior to expiration plots are the same. So that suggests this formula for the relationship between a put, a call, and the underlying, assuming that these are European exercise options so that there is no chance of early exercise. Now, if we also bought the underlying, then we would move S to the other side of the equation. A typical assumption at this point is to assume we enter the position by taking out a loan at the risk-free rate, by selling a risk-free zero-coupon bond short for the full cash value of the position. While we likely would not take out a loan to cover 100% of the position, this assumption is meant to account for the cost of money more generally. Whether the underlying is trading above, at, or below the strike price, the end result is that we would need a zero-coupon bond that equals the strike price at expiration under this simplified model. That gives us this equation. And a plot of the combination of a long put, short call, and long underlying, financed 100% with a loan, seems to support that notion. But to illustrate what is missing here, let's zoom in a little closer and increase the dividend yield to see what happens. While a dividend yield of 20% is quite high, this does illustrate the point. Dividends matter, and so we need some way to account for them. So we multiply the stock price S by E raised to the negative dividends multiplied by time to expiration, which discounts the stock price by the dividend yield, as dividends reduce the stock price once they're paid out. But it is not just the dividends. We also need to account for the cost of the loan, which means interest rates, as we can see here. As we are assuming the loan is actually a zero-coupon bond sold short, we also discount the strike price, K, which is the principal amount of the bond, by the discount factor E raised to the negative of the interest rate multiplied by the time to expiration. Considering both dividend yield and interest rates will give us this equation. So this is saying that a long put option combined with a short call option and a long position in the underlying, including dividends, minus the loan whose principal plus interest is a strike price is equal to 0. Finally, we can rearrange this equation to get two equations, one for the value of a call option and one for the value of a put option, both in terms of one another and the underlying, as well as the loan to enter the position. But what does all of this have to do with option Greeks? Let's start with the option Greek delta and use the put equation to understand how the delta of a call option relates to the delta of a put option. Since delta is the change in the option's value with respect to a change in the price of the underlying, we start by differentiating with respect to the price of the underlying. So the left side becomes the delta of a put option, while the right side becomes the delta of a call option minus the change in the price of the underlying with respect to itself. The derivative of anything with respect to itself is just 1, leaving us with E raised to the negative of dividends multiplied by time to expiration in years. Lastly, the loan and its interest rate never change with respect to the price of the underlying, or in other words, it is a constant, so its derivative is 0. So the delta of a put option is the delta of a call option minus E raised to the negative dividends multiplied by time to expiry. But what does that equal? This plot will help us understand. If the dividend yield on the underlying is 0%, then we have E raised to 0, and anything raised to 0 is just 1. Even if the underlying does have a dividend yield, most dividend yields are in the low single percent range, and the majority of options have less than 3 months to expiry, making the E term very close to 1. So even though the E term is not always 1, many sources will assume that it is 1. But it is worth keeping in mind that dividends can cause deltas to deviate from the typical put delta equals call delta minus 1 shorthand. Now let's look at the delta of both the call and put option side by side. When looking at it visually, the delta of a put option appears to be the delta of a call option shifted down roughly by 1. Let's think about this and make sure we agree with this conclusion. As the price of the underlying rises, the value of a put option will decrease. So it makes sense that the delta of a put option is negative. As for the shape of the delta surface, as the price of the underlying rises further and further, the put option goes further and further out of the money, and so the delta should go to 0 as the option becomes far out of the money. And if the price of the underlying falls, the option becomes more and more in the money, and so the delta should approach -1. And as we approach expiration, the pull to either 0 or -1 should become more extreme. That seems to be the case here, so the plot makes sense. Let's go back to the put-call parity equation of a put option and see what it tells us about gamma. If we differentiate with respect to the price of the underlying, we get the delta. If we then differentiate again with respect to the price of the underlying, then we should get gamma. The left side becomes a gamma of the put option. Then the right side becomes a gamma of the call option. And here's where the symmetry mentioned earlier comes into play. Since e raised to the negative of dividends multiplied by time doesn't change with respect to the price of the underlying, it is a constant and so goes away, and we get that the gamma of a call exactly equals the gamma of a put. But what is the intuition behind the gamma of both calls and puts being equal? Since gamma measures the convexity of the value of an option with respect to the price of the underlying, what it is measuring is the sensitivity in either direction of the value of the option to changes in the price of the underlying. So the fact that the gammas of calls and puts are equal is saying that their sensitivity to price changes is the same. So delta gives us the directional exposure of the option to the price of the underlying, and gamma gives us the sensitivity of that directional exposure. So this tells us that the value of calls and puts move with the same magnitude at the same price of the underlying and time to expiration, just in opposite directions. Now gamma is not the only option Greek where we see calls and puts being equal to one another. Theta, for example, is a Greek which is mostly the same for both call and put options. Let's differentiate the put-call parity equation for a put option again, this time with respect to the time left until expiration. The left side becomes a theta of a put option, while the right side becomes a theta of a call option. Since we're differentiating with respect to t, the dividend, -q, and interest rate, -r, hop down in front of the exponential e. Wait, we didn't get to the result where the theta of a call equals the theta of a put. What gives? Well, the truth is that they are not equal. The last two terms mostly cancel each other out, and so for practical purposes, they are considered to be equal, and we can see that visually. While not technically equal, they do look the same to the naked eye. Let's plot the difference to get a better idea of what is going on here. While the theta plots are intense, the plot showing their difference is about 2 orders of magnitude smaller. So while theta is not technically equal for calls and puts, most option trading platforms will report only 1 theta since the difference is so small. So the big takeaway here is that the time decay of calls and puts is nearly the same, with differences in dividends and interest rates driving the slight differences in theta. Now let's differentiate the put-call parity equation for a put option with respect to the expected volatility of the underlying, which should give us Vega. We get that the Vega of a put equals the Vega of a call, and since the last two terms do not involve volatility at all, their derivatives with respect to volatility are 0. So this means that the Vega of a call is exactly equal to the Vega of a put. and a visual inspection confirms that. The plot makes sense as an increase in volatility increases uncertainty. An increased uncertainty would increase the price of all options, as there is less certainty of where the price of the underlying will end up relative to the strike price of the option. Since we take the present value of the strike price, interest rates do have an impact on the value of a put beyond just the impact of the call option in the put-call parity equation for a put option. Differentiating with respect to interest rates gives us the rho of a put option equals the rho of a call option minus the derivative of the stock price including dividends with respect to interest rates. Well, that doesn't change with respect to interest rates and therefore is a constant, so the derivative is 0. The final term is the loan, which does include interest rates, so the negative t hops down in front. As a result, rho is different for both the call and a put option. In fact, the rho for calls is positive while the rho for puts is negative. But why? Rho represents the interest rate on the hedged value of the option. So if you were to buy a call option, then you would hedge by selling short the stock. When you sell short the stock, you receive the cash value of the stock and can earn interest on that cash value. So the increased price of the call option offsets the interest earned on the cash received from selling short the stock. Essentially, this ensures there is no free lunch. The intuition for why puts have a negative rho is the reverse situation, as the put would be hedged by purchasing the stock. And remember, we assume that is done by taking out a loan for the value of the stock. So the cheaper put premium offsets the interest paid on the loan used to hedge the position with a long stock position. This logic also explains why rho gets more positive or negative as the options become deeper in the money and have more time to expiration, as that will require a larger stock position for a longer period of time to hedge, and so would result in more interest paid or received. Likewise, since the underlying price takes into account dividends or cost of carry, the impact of dividends is not equal across both calls and puts. Differentiating with respect to dividends gives us the fee of a put option is equal to the fee of a call option minus the derivative of the stock price including dividends with respect to dividends, so again the negative t hops down in front. The final term is the loan, which doesn't include dividends, so its derivative is 0. So the fee of a put option is different than the fee of a call option, and we can see that difference visually as well. As expected, dividends and fee are the mirror image of interest rates and rho, so the intuition of how a hedged position impacts the price of calls and puts works for fee as well, just the other way around. Option symmetries, such as put-call parity, allow us to understand the relationship between the characteristics of options on the same underlying with the same time to expiration. One of those characteristics is the relationship between the option Greeks of puts relative to calls, which we explored in this lesson. But these are not the only implications of option symmetries, and so we will revisit this topic again. In the next video, we'll dive right into the heart of volatility trading when we cover delta hedging. I would like to give a special thanks to those who support this channel on Patreon, especially for the comments they provided on early versions of this video.